dear colleagues, can I introduce David Talbot? He is the head of machine translation department in Yandex, and he moved to Yandex from Google. And David and his colleagues develop narrow machine translation in Yandex, and we know that narrow machine translation techniques greatly improved machine translation, and especially fluency of machine translation. And I'm waiting for David's presentation, and I think that it will be very interesting. Please, David.
Thank you very much for that kind introduction. It's my pleasure. Thank you to Andrei also for the invitation. Yeah. Can you hear me okay?
You should go.
Yeah. And can you see my slides okay?
Yes, everything is fine. Yeah.
Great. Okay, so let me start.
David.
Yeah. Can you not hear me? It seems like can you hear me now? No.
It's fine. It's fine.
It's fine. Okay. Yeah. Okay. Thanks, Andrei. Okay. So it's my pleasure. I'm really happy to join you. I'm sorry I couldn't join for more sessions before. And I'm going to talk. I'm trying to, I think, give you an overview of how the field that I work in, which is natural language processing, how that has changed in the last 10 years. And it's definitely an exciting time in the field. There's a lot of cross-pollination between other related areas. And I think it's also an interesting time to consider how these new developments can be used by people who were maybe previously been outside of NLP, but are interested in studying language in a linguistic formalism. Okay, so I'm very happy to take questions during the talk, although possibly I won't. I mean, if there are questions and you put them in the chat, that's probably the easiest way. Then I will endeavor to answer them at the end. I'm happy to answer questions in Russian. My Russian is not good enough to give the presentation fluently, but it is good enough to answer some questions. Okay, so just firstly, what I don't want to talk about. So as was mentioned in the introduction, there has been huge improvements in certain specific tasks like machine translation over the last few years because of the introduction of what I will call deep learning, the new wave of neural networks. And I'll just take that as a given. There has been some improvements. What I want to focus on is not really the hype about that and about where that's really, not exactly where that's going, but how that has fundamentally changed the way that we handle language in this field. Okay, so I just to start, this is from a press release of one model which is called GPT-2. It's a model which was developed by Elon Musk's OpenAI Foundation. And they said when they released this model, well, actually, they didn't release the model. They said the model is too dangerous to be released, okay, due to our concerns. We are not releasing the trained model. I'll be honest, I don't believe that this is really the case. I think this is just a case of very clever PR, okay? I actually think that while, yes, of course, we should be aware of potential misuse of very fluent generators of text, I don't think that many people would be confused, okay? So I think this is really just PR. So I'm not going to really talk about that. I'm going to talk about the sort of fundamental differences. Okay, so my talk has 3 parts. The first 2 are much longer than the last one. Firstly, I would like to just explain how I see the fundamental differences of the new wave of empiricism in NLP. Okay, so this deep learning, which I'll refer to more as an end-to-end learning, what that really means and what are the fundamentally different things about that. The second section, I think, is is more interesting in the sense that it's about the models that we actually now use in NLP, which have been developed by people with some linguistic background, as opposed to the first section, which is much more about machine learning. And finally, I'll just finish with a few thoughts about what are the limits of learning about language from data, because obviously there's a lot of limitations to these approaches. Okay, so just to put us in the picture, to me, and maybe other people would disagree with this very short history, it seems like this is at least the third wave of empiricism, of learning from data in computational linguistics. So you had the first wave around information theory, distributional hypothesis, which was popularized both in the West and in the USSR in these time periods. You then had, I've put here hidden Markov models. That's a simplification, but I think it's fair to say that in the 70s, 80s, and 90s, the most successful applications of using data to build models of language, such as speech recognition and machine translation, were based on basically the principles of hidden Markov models. And since the 2000s, we've had this, this new wave of neural networks where they really are able to do things which other models didn't seem able to do, okay? And that's mostly what we're talking about here. Okay. So first, the end-to-end learning. So deep learning, I will refer to it mostly as end-to-end learning. The idea is just, it's extremely simple in a sense. It's in many respects, the main point of my talk is that the models we use today are actually much, much simpler than the models that would have been used even 5 years ago. And end-to-end learning is the main reason for that. So in the middle here, I have this picture of a neural network. It's just a function, basically, with some parameters. And end-to-end learning is just the idea that you learn your model directly from your inputs to your outputs. You don't have a pipeline of different processes. You don't have different components. You just try to learn the whole thing end to end. Okay, so this could be that we're translating between English and Russian, in which case we'd give English sentences and Russian sentences on the output. Or it could be that we're doing image recognition and we have an image. We don't know what's on the image. On the output, we know that we want to see a cat. So we train the model. Okay. And just to be, so neural networks, I don't really like the name neural networks because it sort of implies some similarity with the human brain, which is really not appropriate. A neural network is just a function. It's literally just a function. You take some input, you compute some function of it, maybe a composite function, and you produce some outputs. That's all it is. In fact, it's such a generic thing that it's, yeah, I think the term neural network is useful perhaps when you're describing how it is, how this function is trained. And the key idea here is that you put some inputs into the model, you look at the prediction, and you compare the prediction with the correct output, and you update the parameters of your network, of your function, to reduce this error. So just very quickly here, hopefully this will play. Here we have an image of, on the left we had an image of the number 5, and a network which tries to recognize that. So it takes the pixels, the raw data, it computes a function of it, multiple steps to that function. It then tries to produce a probability of one of the different numbers. And depending on how accurate it was, if it suggests that the number was a 2, it will back propagate the errors. Okay, so it's basically using calculus that would have been familiar to Newton and Leibniz. There's nothing particularly modern about the mathematics here. Okay, let's go on to the next one. Okay, neural networks for language. That starts to become a little bit more interesting because language is perhaps more naturally treated as symbolic data, e.g. texts. Okay, so you have these identifiers. And with the with deep learning started really with big progress in computer vision. And it took a little while for people to understand how you could apply these techniques to language, mainly because of this problem that language is more naturally represented as symbols. It's not easy to see how you convert it to numbers. But there was a reasonably clear way to do this. That each of your symbols, and the symbols could be letters, they could be words, they could be parts of words. This is something you might need to choose. But those symbols could be represented by a vector of parameters, okay? And we just learn these vectors, one for each symbol. We then learn the network, which takes the input symbols and maps them to some output symbols, for example, in machine translation. And when we come to the output, we have some vectors which we've computed. And in order to work out which symbols we should use, we just find the closest corresponding vector. So, okay, so it's basically this just visually. This is a very common way to break down many of the models that we use. So each of these big boxes here is a neural network. It's really a single neural network. We have on the input side, I saw a cat, word vectors coming in. We compute some big function. It could have many steps to it. We pass it across to the next part. And here we start outputting words. And here, when we output the first word, yeah, we did that by looking at the vector and finding the closest word vector to that. Okay, then video and then kata. Okay, so it's actually a remarkably simple setup. It's a remarkably simple setup, but it's also remarkable that it actually works. Okay. I want to give an example now about how deep learning has actually changed, this end-to-end learning has changed machine translation. And again, this is not about how it's changed the quality. It's totally true that the fluency has become much better. I want to just explain how it's changed the way we try to solve the task and the implications that has for the models we're using. So pre-2013, we had a pipeline approach to statistical machine translation. This was based on data. It was very much using data, but it was not trying to solve the problem in one step. We first trained word alignments on parallel corpora. We then extracted phrases. We then built a language model on monolingual corpora, and we combined these two models to translate. So the fundamental work here was done by a team who were meant to be working on, I think, speech recognition, but decided to have a side project, and they developed statistical machine translation in the late 80s. The idea here is that to translate a French sentence to English, you just want to build a model of the probabilities of English sentences. And you want to find the English sentence that's the most probable given the French sentence. They used this approach of turning that round with Bayes' rule and said, let's train a language model of English so that we know that the translation we're producing is a good piece of English. And let's do a reverse translation model because that will be easier to apply for various reasons that I maybe won't go into just now. They train the language model on English, monolingual data. They translate the translation model on parallel data. But the fundamental problem they faced was they didn't know how to build a model of French sentences given English sentences. This just seemed like a too complicated problem, okay? What they came up with was the idea of word alignments. So here you have an example of a parallel text, two sentences, English and Russian in this case. This is the data. We have many millions of examples of such sentences that we need to train on. What Brown and et al. Said is that you should have word alignments. You should learn these word alignments. This is possible to do with techniques that are basically the same as hidden Markov models. And once you've learned this word alignment, which you can learn to some extent, of course, it's not always precise. This is a rather easy example in that most of the words do correspond to a single word in the other language. It's not always so simple. So it didn't always work perfectly at all. But once you've learned this, you could then factorize the probability by making independence assumptions. So essentially, at this point in statistical NLP, people just felt like you had to make many simplifying assumptions in order to learn and to build a model. And here the simplifying assumption is that each of the words in the Russian is generated only dependent on the English word to which it's aligned. Okay, so we made a huge assumption. Yeah, this is obviously completely wrong, because if you look at the word ustala, yeah, it's clear that this word does not just depend on tired. It also depends on the gender of the word it, which in turn depends on which of the two nouns this it refers to. So there's a lot of going on, and this model completely cannot capture that. Okay, and this is, I think, a good example of why the previous generation of machine translation would almost certainly get the agreement wrong in this sentence. Okay. So these are the phrases we would extract, and this is how we would translate it. Okay, post 2013, there's almost nothing to say. It's so simple, the model. We just train a model to translate directly from parallel corpora. We learn the distribution directly. We make no explicit independence assumptions. We just take the words, compute the function, and output the vectors. And basically, if we situate what's been happening in deep learning in NLP, in deep learning in general, with what's been happening in NLP, well, we see that similar trends. So basically, as the models became deeper, it seems that we were able to build models that start off by computing quite local features, and later layers in the model can do more, can produce more composite features. We'll talk about that in more detail. I think it's also just interesting to consider, why did it happen now? Why is deep learning become such a big thing? Why has it had so much success right now? Neural networks and the basic algorithms existed since at least the 70s, if not the 1770s. In fact, 1670s. I think the main reason is that people were just convinced that you couldn't solve these problems directly. That this is meant to be a picture of the error surface for optimizing one of these models. And the point of this picture is that it's many peaks on this picture, which you could end up getting to with your optimization. And yet you wouldn't get to the main peak at the back there, which is taller than all of them, because you have lots of local optima. Okay. But I think the key things are that people came up with, and mostly this is Geoffrey Hinton's group, they came up with new regularization techniques, better optimization algorithms, and it has to be said, there's a lot more data now and a lot more computational power. So I think that's probably the main reason why we see these practical applications of these models now. Okay. So what's the implication of doing end-to-end learning? I think the key implication of doing end-to-end learning, particularly of interest for language, is that you end up learning the representations of the data that you're modeling. Okay, and this is interesting, I think, from a linguistic perspective. So since we just learn vectors of parameters for each symbol that we're working with, we don't decide a priori what is important and what isn't important. We just learn a representation that is important, that is useful for the task which we're trying to solve. So pre-2012, we use symbolic representations, basically arbitrary identifiers, integers, which we would assign to each word. We would sometimes use normalization, like stemming or lemmatization, but basically it would look like this. You would have 4 different words, say, and you would have 4 pretty arbitrary identifiers. If you normalize them, you might end up with something like this, where the representation for dog and dogs is somehow similar, and for cat and cats. But this is really, it's not very generic. It doesn't work for many languages, and it's a bit messy. Okay, post 2012, we learn these representations, and we find that if you look at the vectors that you learn in this process, for example, for learning a machine translation system, you'll see that you learn some interesting patterns on the words. So for example here, this is slightly simplified, but I think it gives you the fundamental idea. If these are learned representations, each of these three colors corresponding to each word, then we can see here that we have one column that seems to refer maybe to animacy. All of these words refer to animate objects, and maybe this column could refer to animacy. The second column could potentially refer to the felineness. How much is this entity like a cat? So the cat and the cats have this to the same degree. The dog and the dogs have it less. And perhaps another dimension would encode some syntactic or possibly semantic number. Okay, so it's very possible in such a distributed representation with hundreds of such parameters that you get some different structures being learned. And this is a very, I think, well-known phenomenon that with these models, you can often find that certain structures emerging in the space. So for example, here, each of these dots is one of the parameter vectors for the word. And we find that the difference between man and woman here may be roughly the same as the distance between king and queen. And then on the right-hand side, a completely different concept, a verb tense shift, which might also be roughly or approximately encoded in the space. And these are things which we didn't set out to do. They're just things that you can observe, and it's interesting to see what we can actually, how we can use these observations. Okay. I want to, I just want to say something about what it means for deep learning to have become so widely used across different fields of machine learning. So for example, today, if I talk to a colleague who's doing computer vision, it's extremely easy for me to explain what I'm doing. There'll be a few questions about differences, but it's extremely simple for that other person to understand, and vice versa. We can really easily share insights across different fields. And that's very, very powerful. Okay, so one of the big advances in NLP in general, with the advent of deep learning, is the idea that you can build a quite complicated pre-trained model of language. So basically all of these rather overhyped models for doing many, many different tasks are based on the idea that first you train a really huge neural network language model just on text. You train it on huge amounts of data, and it doesn't know anything about the task you're trying to solve, for example, machine translation or sentiment analysis, or any task really that relies on some information in text. But because you have this generic language model, you can then just add a very small additional part to your layer. You still train this end to end. You don't train them separately, but because this generic language model already understands how to do many things, such as anaphora resolution, such as it can understand synonyms to some extent. It can compress the language data in a useful way that appears to be quite generic and is therefore applicable to many different tasks. And this is a really interesting idea. This is, I think, a really interesting idea because it brings us towards the idea of really using generic models of language to try to solve lots of different applications. Okay. And finally, just to reiterate on how this has changed, how this has simplified the field. While it might seem that neural systems sound rather complicated, actually they are orders of magnitude simpler than the systems they have replaced. So an MT system from a machine translation system from 2005 probably had 100,000 lines of code. And actually, even the people who worked on that project probably didn't all understand exactly how all of it worked. Today's toolkits for doing deep learning allow you to implement a machine translation system that is significantly better than that one from 2005 in 100 lines of code. And it's relatively easy to explain to somebody who has high school mathematics what it's doing. Okay. Yes, it does need some programming skills, but I think I'm trying to make a relationship here between computers used to be something only for real specialists. Yeah, only programmers would use computers. But sometime in the 80s, that sort of changed. Computers became, in a way, they became much more complicated underneath, but they exposed an interface which was much simpler for a user to interact with. And PyTorch, which is one of the more popular toolkits for doing deep learning, while it's not easy to use if you don't have some programming background, it is much simpler to use than anything prior to it. And so I think this is a really interesting trend we're seeing, that basically the barriers to doing data-driven linguistic analysis and computational linguistics and natural language processing, those barriers are really becoming smaller and smaller, which is very nice. Okay, so I just want to make sure I get my timing all right. So that was about deep learning in general. What I want to do now, this section is about how, with deep learning, people who are mostly focused on natural language have made some contributions which I think are interesting in terms of the way they propose models which are interesting, I think, from a linguistic perspective. I'll explain that slightly better. Sorry, this is, yeah. So the idea here is inductive biases. So when we do anything which we're learning from data, when we're trying to learn a model and we want it to generalize, we show lots of examples. But if we don't have some assumptions about how these examples relate to one another, then it's impossible to generalize. So just very simply, if we show example sentences for translation, if we don't assume that in the same context, the same word will probably have the same meaning, if we don't assume this obvious assumption, then we can't generalize to new sentences. Now, in the previous generations of models, we used to try to impose these biases, these assumptions, by doing some manual feature engineering. For example, stemming or lemmatization, or using a syntactic parser to give us some structure to a sentence. In the deep learning field, we tend not to do that, but we have to still make decisions about what's the structure of the model we're going to use. And this is where there's been some interesting contributions, I think, from NLP, which have actually gone from NLP back into the broader deep learning community. So I think it's fair to say that from 2010 to 2012 to 2017, NLP was just a consumer of deep learning. And I think since 2017, the NLP community has become more of an active producer of contributor to ideas which maybe have applications beyond NLP. So what's the idea here? The idea here is really very simple. Some bits of this will be a bit detailed, but the idea should be very, very simple to follow, I hope. So I mentioned that you have this thing called an encoder. This is basically just building up a vector representation, a sequence of numbers, if you like, to represent this sentence, okay? And the question is, how does this encoder actually do that? Okay, so this is the most, in a sense, obvious way to build an encoding of a sentence. The sentence consists of a sequence of words. You take the words you take the first word, you take the second word, you compute a function which is now, this is now a representation of the first two words. You then add another word, you get a representation of the whole three words, you add another word, and this is a representation of the whole sentence. This is known as a recurrent neural network. They've been around since, I guess, at least the 80s, if not before, and seems like a very natural way to encode a sentence. But you'll see that it has this real bias towards the sequential order of the words. And I think as linguists, you'll appreciate that this is not a particularly efficient way to treat language. So for example, if we want the word saw and the word cat to somehow interact in their representation, this information has to pass through the word for, the indefinite article a. That doesn't really seem like the most natural way to do it. And actually it has practical problems. We found quite early that this approach to doing machine translation, while it worked for short sentences, it really didn't work very well for longer ones. And so the first point here is there's a bottleneck when you use this kind of sequential bias in your model. And it's not a natural model for language. I mean, we all know that language has a much more complex structure. I mean, sometimes it can be represented in some form of tree or even in more complicated graph-like structures. So the first idea is very simple. It's called attention. The idea here is that while we're processing the data here in the target language, we allow the network to make arbitrary connections back to words in the input. Okay, this allows it to short circuit the information path, the sequential path. Sorry, and this is a very natural bias, I think, for machine translation, because it corresponds quite well to the idea that the assumption that when translating, not all of the words in the input sentence are equally important when translating each part of the sentence. Yeah, so it's probably, this is a very simple example, but it's sort of reasonably clear that when you translate the word cat here, you probably only need to know the word cat and maybe the context of it as being next to a verb to get the right case. Okay, so this is attention. It's definitely very powerful, and it made a huge step forward in the performance as well. There's actually a much more important application of attention, and this is what I'm showing on the slide here. So the idea here is that now there are no sequential connections. Okay, this is the sentence. This is just an encoder. We're trying to just build up a representation. We could use this as part of a machine translation or a language model. And the idea is that we process all of the words in parallel. We process them in parallel and we allow them to pass information between one another. Okay, so each of the words is allowed to look at the other words and basically say, at this point, I'm kind of interested in finding out what's this word over here. Okay, yeah, that looks like it's important for me. Give me some information from there. And then it passes it on, and it does this multiple times. So at each step, any word is allowed to make a connection to any of the other words and to obtain some information. And we build up a representation of the whole sentence in this way. Okay, so at this level, we still have 4 different representations corresponding to these 4 different positions, but hopefully at this point, this representation here will know a lot more about its syntactic context. It will know that its object maybe is animate. It will hopefully know that if we're training this to do machine translation to Russian, it should almost certainly know the person or the gender of the subject to its left, because this is all information it will need to do translation later on. Of course, it's not explicitly told any of that, but as we will see, this is sort of the kinds of things it learns. So self-attention is just the idea that you allow information to flow between any 2 positions in your model, and you learn these dependencies. So it definitely has something in common with dependency parsing. There's no real tree structure here, but it's totally parallelizable. And I think it's hard to overemphasize this last point. This is, in my view, the first really successful, and it's amazingly successful, model that has no innate sequential bias. Okay, and in computational linguistics, in NLP specifically, we've always ended up using these sequential models. We knew they weren't a good model of language, but they always were easier to build, and they always just worked better. And at last, we don't find ourselves in that slightly embarrassing position. Okay, so yeah, I don't want to take up too much time. So I'm just going to quickly go through how this attention works. This bit is self-contained, and if it's harder to follow, don't worry. We will come back to a slightly simpler part afterwards. So just to show what's the inner workings of this intention mechanism. So here we have the first layer with the vectors, the x's, which I put into a matrix here. Basically, we transform this matrix X 3 times to get queries, keys, and values. We then basically treat each word in turn. Here I'm just focusing on the word saw, and we compute some distribution by looking at how similar these different vectors are to each other. And in this case, under this transformation, we see the word saw has the largest affinity with cat, which means that it will pull in more information from the word cat, okay? Now, last but very important point is, in these models, we don't have to do this just once. We can actually do it multiple times in parallel, because this attention mechanism is only able to really look at one place at a time, and it only pulls in the information uniformly from that position. So if this connection here, we refer to each of these, each attention component we refer to as a head. Okay, so I'm not sure where the terminology came from, but it's called a head, and I'll use that term. So the first head is looking at the object, and maybe we could compute a second head which looks at the subject. Okay, so in parallel, we're able to pull in information to our representations from these different places. And each of these transformations can look at different places, can look at different dimensions. Okay, so just to give a concrete example, in Russian, this is not a natural dependency parse at all, but this could be one way in which we get a connection here, which enables the model to understand the case. Thank you. The case government of this verb, занимается новым, and also here this might be another attention head which might be capturing the gender number agreement between these two words. Okay, it could also be this way as well. Okay. How does this actually affect translation? So this is a sentence which the most difficult word in this sentence, the animal didn't cross the street because it was too tired. The animal didn't cross the street because it was too wide. I hope you all appreciate that the most difficult word in this sentence for translation is the word it, because you have to solve the anaphora in order to appreciate whether what noun it should agree with in Russian. So here we see that that actually with this transformer, this self-attention network, we're able to do this resolution. So we see that animal животное is neuter, so we have устал. And the same here, when we change it to wide, it quite consistently will get these anaphora resolution problems correct, because it's learned that these connections are important. Yeah, and this is something that you don't even see all the time in other deep learning models which are not based on self-attention. Okay, so this is something that I would claim the performance on these kinds of specific examples definitely increases with self-attention. Okay. Okay, we've got a bit of time. Let me just quickly go through. This is some work with a colleague of mine from last year, where we basically looked at these attention heads in some machine translation systems. And the main thing to look at here is that what we found was that actually quite a lot of the time, the head, a subset of the heads are looking at very specific syntactic relations. So here, the baseline is just, I imagine the verb, the baseline is looking at the word next to it for the object. We see that we have a head which looks at the object almost 80% of the time. So it does seem to be paying a lot of attention to objects. And we find this sort of holds across different languages, that the model does look at verb subject, subject verb, verb object, and object verb relations. Okay, And we basically found, just to summarize this slide very quickly, we basically found that if you look at these models and you understand which of the components are most important for the final predictions, you find that these are the most relevant ones. Yeah, they're the ones that are, we had a way of measuring how much these particular components influence the final decision of the translation. And then we looked at how confident these heads were. So how much of the time did they assign a very high weight to a specific position? And they were very confident. Okay, so far so good. We also found that there quite many of them have quite interpretable functions. So these purple ones were components that looked at positional words before and afterwards. Remember that the model has no prior bias towards position, and these green ones are the syntactic ones. Okay, just finally, finally in this part, I just want to show this other result, which I think is kind of interesting, and this is how the representations in the different layers of this model change. Okay. And we looked at 3 different tasks: machine translation, language modeling, and masked language modeling. This is like the closure task where you have a missing word and you have to try to predict it. So here we have 4 different colors for 4 different very frequent types: is, are, was, were. And on the top layer, we have machine translation, the representations at the lowest level going all the way up to the top level. At the lowest level, they're quite distinct. And what we see is that by the top level, there's still a distinction between the red and the yellow, which is the tense. So red and yellow is are, and blue and light blue is was, were. Whereas for language modeling, we see that this distinction is really much, almost, well, it's disappeared to a large extent. For masked language modeling, we see I think what's the most interesting thing here we see is that to solve the masked language modeling problem, where you just have to predict a word missing in the middle of a sentence, it appears that the structure you need to learn is much more to do with disambiguating everything. Okay, so we see here that at the beginning we have the words which were masked, which are therefore the colors are all overlapping, and gradually, as it goes through the different layers, by the top layer, many of the tokens which correspond to have moved towards the correct color. And just the last one on looking inside the transformer. This picture shows the word, lots of different sentences, the representations of lots of different sentences, the word is in those sentences in different syntactic contexts. And the coloring here, the closer the syntactic context for the word is, the closer the color. Okay, so we see at the beginning, the model knows nothing about the context, it's completely context-free, context-independent. And gradually, as it goes through the model for machine translation, it clearly has to distinguish different syntactic contexts, showing us quite clearly that this is an important part of doing machine translation. For the language model, interestingly, this is much less apparent. Yeah, so the different contexts are still completely mixed up here. And again, the masked language model, the closure task, is in many respects much similar to the machine translation. Yeah, there's a lot of disambiguation going on there. Okay, so yeah, so basically this is a really growing area. It's a very new area, but it's an area which is now attracting a lot of interest in NLP. Is how can you use these models to actually look at understanding how the different tasks, such as machine translation, language modeling, how they differ, and what auxiliary linguistic disambiguation tasks they require solving. Okay, this last part is very, very short, so I think I should just about make it in time. So, the limits of learning from data. Okay, so I just want to point out that a lot of the excitement, while I don't want to detract, there has been huge progress in many applications. Any of you who've used a machine translation, public machine translation system, such as Yandex or Google or Prompt, you will have seen that the fluency has dramatically improved. But the excitement does tend to focus on the average performance of these models on fixed data sets. And deep models can produce extremely strange results sometimes. Okay, so we need evaluations that can account for these. And it's rather difficult because they're quite rare, these strange results, but they're hugely important because they completely break the illusion of intelligence. And a major part of this is because the models are not very robust when they're applied to out-of-domain data. Okay, this is a huge problem. And basically, well, sort of finally, really, I've got two, there's one more slide, but this is from a paper at the ACL, the Association of Computational Linguists conference this year. And it was a very interesting paper where they basically, they tried to encourage people in the NLP community, and I think quite correctly, to be careful about the words they use when they talk about these systems understanding something. And their claim is, I think, reasonably irrefutable, that any system trained only on linguistic form cannot in principle learn meaning. Okay, we can find interesting correlations, but we're not really learning meaning. Okay, and that actually a lot of the meaning which people seem to find in these systems is actually projected by the humans who try to interpret the data that they get. So you look at a translation and you have a big context about it, and you understand it, and it seems like the computer understood what the text meant, but maybe that's not the case. And this is the last slide. So I think this is an example. I hope you can read it. So this is an example of I think GPT-2, one of these really, really huge language models. The first sentence is the first sentence of the English translation of Kafka's Metamorphosis. The rest of it, which is underlined, is what was generated by GPT-2 or 3. And it's remarkably fluent, but it's really quite easy to see big problems with it. So if you look at this, okay, so he awoke one morning, he found himself transformed into a monstrous vermin. Okay, so far that's Kafka. In the days to follow, and until he awoke in this way, it was unclear how the nightmares had affected him. The concept of time in this sentence is very hard to parse. I mean, it's fluent, but it's not like what's happening exactly when, not very clear. After he slept a week and a half, his nightmares continued, but the order here seems slightly wrong. And then if you carry on, so in the first sentence, it was pretty clear that it was Gregor himself who'd become a vermin. But gradually it turns out that the computer seems to think that the monster is somebody else. And this sentence, I think the last one I want to comment on is this sentence here. The monster, it tore off the head of Gregor's bed. Now, this almost fits the story perfectly, but it's completely confused in another sense. So we see here that the model has learned that monsters tear off heads. Yeah, so far so good. It's also learned that beds, in English at least, have something which we call a head. But tearing off the head of Gregor's bed and then eating the body, this doesn't make any sense. But to be honest, if you read it very quickly and you were in a positively inclined, you might be quite impressed with this. But I feel like there's not too much to be that impressed with apart from the fluency. Okay, so I'll leave with that example. I've finished now. Thank you.
Thank you very much for your comprehensive and inciting presentation. Please, questions from audience, as I understand, in Russian or English.
Yeah.
So, questions? And I currently do not see any questions. Therefore, I would like to ask.
Sure.
I read your article about the combination of all the machine translation approach, such as phrase-based and new. Can you comment on, give some examples on this interesting combination? Why we need all the...
Yeah, so actually we need it precisely for the problem of robustness. So what we notice is that the older phrase-based machine translation is much less fluent, but is usually more
accurate.
Yeah, well, maybe I'm not sure it's more accurate exactly, but when it's not able to make really crazy mistakes for the whole sentence. It can make specifically bad mistakes, but it's unlikely to do it for the whole sentence. The neural system, particularly when it's not trained properly, can occasionally generate just complete nonsense that's unrelated to the input at all. And so what we did is we built we know that this happens only quite rarely, but if it happens in our public system, a user who sees that will completely fail to understand. Well, will probably never use us again. Probably that's one person we lose to Google Translate. So we just had the idea that we use a classifier which basically looks at the translation and says, does this translation look like it's reasonably close, like that it's translating most of the words in the input. And in those cases where that didn't seem to be the case, we would just switch to the phrase-based system. So when we first launched the neural system about 3 years ago, we needed to do this for, I think, 5 to 10% of the translations. Now that proportion has gone down as we've managed to train the neural system better, and used other techniques to make it more robust. But it still is. It's still important.
Thank you. I see that there are questions, and Andrei, please, your question.
Yeah, thank you so much, David, for a very illuminating talk. And
thank you.
A whole number of questions, but let me just start with one.
Sure, sure.
Yeah, let me put it this way. You mentioned assumptions. So when you produce or plan machine translation systems like that, you make numerous assumptions. For example, the assumption that translation can progress sentence by sentence.
Yes, yes.
This sentence and the next one.
Yep.
And I think that often developers of artificial intelligence systems, they make all kinds of assumptions that from the top of their heads.
Yeah.
Actually, but on the other hand, we see this. These kinds of data-based systems are extremely powerful and effective. Do people creating these kinds of systems actually need expertise of linguists? Is there anything linguists know that is helpful for modern machine translation?
That's a really good question. So I don't know. The short answer is I don't know, but what I can tell you is that when I first started working in statistical machine translation around 2002, at that point, there was a somewhat similar optimism around statistical methods for machine translation. And I went to my first ACL conference and I saw these two guys who were wearing t-shirts, and one of them said, "I won the syntax bet," and the other one said, "I lost the syntax bet." And I said, "What's this syntax bet?" And the point was they'd had a bet, could you use syntax to improve machine translation? And in 2002, they had decided that confidently that you could not use syntax. Now, the guy who was wearing the one which said, "I won the syntax bet," who didn't believe in syntax, 7 years later, he was my boss at Google, and Franz auch. And I helped him introduce syntax into our English-Japanese system because it was really, really important. And he was very empirical. Once he saw that it worked, he was very happy for it to work. He didn't have any prejudices against it, but he didn't believe that it was necessary. Now, I think at the moment, neural machine translation is in that kind of situation. It's clear that we do use some insights about language, because you'll see, for instance, if you just look at the neural machine translation system built by Chinese developers, it will generally be better for Chinese, because they've made some decisions there that are maybe not very clear, but probably make it work better for Chinese. But I believe in the longer term, we'll definitely see linguistics coming back into the picture. It's just that we have the new models, we have lots of data that will plateau, and then at some point, using intuitions and using some prior knowledge about language will become more important again. So just maybe need to wait a year or two.
So, thank you for your answers. And we have a question from Irina, as I understand. Please, Irina Frost. Yes? No? No?
I think
No, so sorry. I'm sorry, I just confused for a moment. I would like to ask about to be honest, I remember that some scientists from Dublin University also worked on the machine translation systems. They decided that it's a huge difference between statistic and neural machine translation, corresponding to the languages, to different languages. And when we are speaking about languages with rich morphology, statistical machine translation, they definitely have some advantages. They are more fluent and more accurate. As far as I remember from the papers from 2018, something like that. So what do you think now when you are working on the neural machine translation for Russian?
So to be honest, I would suggest it's actually the opposite. So we see that the neural machine translation system, it works much more like a language model in the sense that it tries to generate very fluent text. And this is why it's been really amazing to be working at Yandex, because obviously the most important language is Russian, and morphology is super important. So I actually think that for Russian users of machine translation, the improvement from neural is much more obvious than, say, well, I don't know. I mean, English and French, you would have seen some improvements, but it may be less obvious. The point is that the statistical system, the way it does it, it takes the input sentence and it literally breaks it down into chunks and translates each part separately. And it keeps a few different possibilities for each part and tries to piece them together with a language model. So it's got like, you've got the word like videl and koshka, koshku, koshka, and it's trying somehow to find, but this can work for very local things, but once they're far apart, the language model is not able to piece it together. So I think you're right to say that the impact is different for different languages, but I would say that it's actually the morphology that's got better.
Okay, thank you.
No problem.
Thank you so much.
I know that there is a question again from Andrei, but do we have any questions from somebody?
Поднятая рука Ирины Подгорбунской.
Please, please, Irina, I couldn't see. Please, Irina, other Irina. Please.
At first, I would like to say that it's a pleasure to know David, and thank you for your presentation. And I have a question. You explained us a simple example. He saw a cat. Well, I saw a cat.
That's okay.
I saw a cat. And for example, you know, there are a lot of phraseological units in each language. And this sentence, for example, he always, her, eats out of his hand. He always eats her out of his hand.
Okay.
And how does the machine translate this sentence without context?
Without context. Okay. So he always eats her or feeds her?
Eats
Okay.
her out of his hand.
I'm not sure how, yeah?
In Russian он всегда кормит ее с руки.
То
есть он ее приручил. Он ее приручил.
Yeah.
And how does machine translate?
Well, without context, so I think my general answer would be that we have clearly come to the point now with machine translation where we can't translate. We can't really afford to translate without context. So exactly at the moment in Yandex, we're working on changing the system so that when somebody gives us a sentence without context, because they do, then we will try to give multiple translations, okay? And in parallel to that, we're actually trying to incorporate context into our translations when it's available, okay? Because I think the first question a human translator would be, a human translator would want some context. They wouldn't want to commit to one single translation without some background information. So the model without the context will just produce whichever seems to be the most common variant on the which is not always the most useful one. Yeah? So context is a big one, and as Andrei mentioned, this assumption that each sentence is translated separately, it's a hugely simplifying assumption, and in the past I think we ignored this assumption because the quality even within a single sentence was not so good. So we just thought, let's try and make it a bit better before we try to solve a more difficult problem. But I think we came to the point where we need to start to use context, because that's where the improvements will come from.
Thank you. I see. Thank you.
Yeah, no problem. Thanks for the question.
And I saw a question from Andrei Vdovichenko. Andrei, do you have?
Yes, sir. Do you can you hear me? Yeah.
Yes, I can. Yeah.
Yeah. Thank you. Do you agree that we merely understand context, not words? If we assume that it is impossible to understand a word without context, we should conclude that we cannot understand a word in itself. By itself, not clear what it means and something like this. Yeah. So I think that in this way we could explain the situation when the phrase is sorry. Excuse me. When the phrase is not so correct in a language you use this moment, but you understand a speaker. This is the explanation is that we understand the cognitive state of a speaker at this moment. So I think that any computer processing is a helper for making understand the cognitive state of a speaker of a person who is making a communicative impact in the moment. Yeah, so that's why I think we don't we should not pay so much attention to the correctness, to the full correctness of the verbal form, of the syntactical or something like this. But yeah, I mean, there is a margin.
So if I understand you correctly, I think it's something I definitely agree with. Just in a very practical sense, in Yandex, when we're evaluating the quality of our machine translation, I mean, it's really hard to evaluate machine translation because unlike other problems in machine learning, when you have a single sentence or a single document, there are hundreds or thousands or even millions of correct translations for the same thing.
Yeah.
And what we want to really focus on, we want to understand, okay, we are presenting the translation to a specific person in a specific context, and they have a specific purpose in using this translated document or something. And have we succeeded in helping them achieve whatever goal they had there? So it's a little bit different from what you're saying, but basically, we want to move away from trying to evaluate machine translation, just like, did you get the right words in the right order? But did you actually allow a person to do something or to make some decision that they couldn't have done without the translation? So
yeah, thank you.
No problem.
Thank you very much to David, and
thank you very much.
Audience for questions, for interesting discussion. But now I think we should finish this session and to have some rest for next sessions.
Okay.
Thank you so much, David. It was fascinating. Yeah.
Thank you. Thank you very much for the invitation. I'm really nice of you to invite me, and I really enjoyed your questions.
For your interesting presentation. Thank you.
Okay, thank you. Okay.